What's up guys? I've been wanting to make this video for ages but didn't have a way to do voiceovers anymore, so let's get into it. Let's talk about bearded dragon morphs. So a morph is going to be a genetic mutation resulting in a different colour, pattern, scale, type, whatever, at least for the purpose of this video. So let's get into it. First up, we're going to have normals. You may hear some people refer to these as wild types, and that is because it's how they naturally appear in the wild. So if you went out into the Australian outback, that is what you would find normal central bearded dragons. That's not to say that normal bearded dragons can't be absolutely stunning. So as you can see on the screen, they come in a variety of colours, even in their natural form, and that's going to be greys, browns, golds, even through to some oranges and reds and stuff like that, which leads us on to high reds. Now these are all the rage at the moment, and they are technically a normal, at least until you add other genes in. So these are going to be normals that have the most red possible picked out and selectively bred together to produce babies that have even more red. This continues on generation after generation to produce these high red lines. Now this can be done with any colour trait, like we've seen it done in the past with citruses. Those were animals that had more yellow and blue and stuff and then bred together to make more citruses, and that's what we gave them the name of. You've also got traits like larger lizards in the example of German giants, shorter noses, and all other sorts of morphs that aren't actually morphs. They're just kind of designer line-bred lizards, which can actually be harder to produce than some morphs sometimes, and you'll see why in a minute. So for our first actual morph, we're going to start off with leatherbacks, and those are simply just lizards that have smoother scales. So they have a gene which smooths out their scales and changes the shape. So I've did my best to do a little drawing to show you the rough idea. But it's something that you can visually see when you put a leatherback next to a normal scale, that they have these smoother scales, less pronounced spikes on the sides, and stuff like that. Next up, while we're on scale types, we have silkies. So that's the top lizard in this photo, and I put these two in a photo together so that you can kind of see the difference, that is a totally smooth, silky, soft lizard. They almost feel like a velvety skin, maybe like the back of your earlobe. They're really, really nice to touch. It's just a totally different texture. Some people think that these need more delicate care, that they need to be moisturized and stuff. I'm telling you now, that's an absolute lie. If anything, you would just want to be a little bit more careful of them being chewed on by crickets, but you don't really want crickets chewing on any of your lizards, right? So it's just common sense. Next up, we're going to have one of my favorites, the Hypo bearded dragon. That's short for hypomelanistic, which means reduction or elimination of black pigment. So the way that that's going to present itself is usually a pastel or brightly coloured lizard, but lots of yellows, oranges, reds, blues, purples. Sometimes hypos can come in almost whites, very similar to the zeros if you've seen them. It really just depends on the selective breeding, but most people have lent towards selectively breeding, like those reds, towards bright colours. This is going to be one of those types that is super easily identified by the fact that it has totally clear nails. So where you'd normally have a black stripe at the front of a bearded dragon's nails, it's just going to be totally clear all the way through with no black pigment. The next morph you might have seen around and not known what it meant is trans, which is short for translucent in this case. And that's going to be a gene that affects how much pigment is in the skin scales, depending on whether it's a silky or a normal scaled. And it's going to result in typically deeper, warmer colours. Think like rich yellows, oranges, reds. Often they have a really nice peach base colour. But yeah, this is going to be another morph that is super easily identified because they have solid black eyes when they have the translucent gene, and they also have this really bluish belly like you can see in the example on the right. Next up is another one of my favorites, and that's going to be Dunner. So that's going to change the pattern mostly. So you're going to get more of a spotty or stripy pattern that's really quite different to a normal pattern when you put them next to each other. And it's also going to change the feel of the scale. It's going to make them feel a little bit rougher, and that's because on a microscopic level, it actually changes the shape of the scale. Some people have also noticed that they may have longer forearms and stuff like that, but that's not the traits that you kind of look for in a Dunner, if that makes sense. Dunners are going to be super easily identified by the scales pointing in the wrong direction on the chin and the belly scales going in different directions, and also by their pattern. Once you get better at getting to know all the morphs, you'll also be able to tell just by touching their backs with your eyes closed. Honestly, it's that easy once you get yourself acclimated enough with them. But have you spotted the different direction scales? There they are. So if you pause now and have a close look, you'll see the scales go in totally different direction to what is standard. Those arrows kind of point out that the chin scales are going up and out, the belly scales are going in every random direction. And just to be clear, on a normal bearded dragon, the belly scales all go in one uniform direction typically. So those are going to be the main genes that we're going to talk about, and we're going to talk about how they interact and how they work in breeding and how they work in combinations. You can combine any of the genes like hypo and trans to make a hypotrans, trans and dunner to make a transdunner. You can combine 3 at a time, hypotransdunners. You can combine 4 at a time, hypotransdunner leatherbacks. We're not so much going to focus on some of the other morphs such as wiblets and zeros because I am focusing more on an Australian audience, and the zeros and wiblets that are in Australia haven't necessarily made their way here by legal means, and I'll kind of leave it at that. Great, so now you know what the genes are, but how do they work and how can you calculate what you're going to produce by pairing up 2 lizards, and how does that whole system work? We can get into that in just a second, but this is where I suggest that you grab a pen and paper to follow along a little bit easier. DNA is split into the 2 sides of the helix, so you can think of the helix as being similar to a ladder, and each step of the ladder carries a trait for a specific thing. So we inherit one side of that ladder from each parent, kind of like the idea here, pink from the mum, blue from the father. And each parent has its own set of DNA consisting of the 2 sides also, and that just dates back and back and back through grandparents, great-grandparents, etc. So if we use gender as the example, we have the X and Y chromosomes. So we're going to really oversimplify this by saying that being male is kind of similar to being a codominant trait. We only need the 1 copy of the gene to be male, which is going to be the Y chromosome. So then in this really oversimplified example, a female only has X chromosomes without the Y, and that's what normal type gene in bearded dragons is going to look like. So it's just 2 copies of the same gene, and it's the base gene. A Punnett square is what this odd looking little table in the corner is. So right now we're going to use the top to represent the genes coming from the mum and the left side to represent the genes coming from the dad. So if we take those letters and we apply them to the Punnett square, we can calculate the odds of what gender might be born. We're going to fill out each square with 1 gene from each parent. So we're taking the X's from the mum down, and then we're going to start taking the X and the Y from the dad across to fill out all of those squares. Each square in the Punnett square represents 1/4 or 25% of the babies that the pair can produce, whether it's through one breeding and multiple offspring produced in that one breeding, or it's through multiple children in the case of humans. So in this example, we can see that the top row is all XX, meaning they are female, and the bottom row is all XY, meaning they are male. So there is a 50% chance of females and a 50% chance of males. So if you remember, we said normal bearded dragon was kind of like the female DNA type, so we can show it as an NN. We said leatherback is codominant, so like the male DNA, we only need 1 copy of the gene to show as a leatherback. So instead of XY, we're going to show that as NL, L being the leatherback gene. So we can take those letters and apply them to a Punnett square once again to see what happens if we breed a leatherback to a normal. As you can see, once again, we have a similar split. Top half are going to be leatherback and the bottom half are going to be normals. So that means that if you produced 18 babies, 9 leatherbacks and 9 normals, at least in theory. But what happens if we breed a leatherback with another leatherback? So we can take those letters, the LN and LN, and apply them to the Punnett squares again. Go ahead and fill out all the slots, and you'll see that we have an LL, 2 LNs, and an NN. So that means that the LL is going to be the Silkies created from the pairing, which is a double copy of the leatherback gene. Now, aside from that, you've also got 2 squares worth, so 50% being leatherback, and 1 square worth being normals. so 25% normals. Hypo and trans genes are going to be a little bit different because they are recessive. That means that they need both copies of the gene to be visually carrying the trait. So if they only have one copy of the gene, this is what we call a het. It usually means that one parent had the gene and the other was normal. A het can produce babies that are normals, hets, or have the full trait. So let's see how that works. First, we have a visual hypo to a normal pairing. So we're going to get all HNs, which is going to be a het in this instant. So they carry the gene but do not show it. You would not know that a hypo was one of their parents. But if we breed a het hypo like those babies back to a visual hypo, you can see we do get some double H's, which is going to be the full hypo, and then we also get some more hets. About a 50-50 split. If we breed a het to a het, this is where things are going to slightly change. So if you have a close look at our results, now we have produced hypos, het hypos, and normals, but normals and hets look the same, remember, so we can't actually tell who's who. Now, because these babies all look the same, we can only say that there's a 2 in 3 chance that those babies that appear normal are het hypo. Converting that to a percentage, it's going to be a 66% chance, and that is what is meant by a 66% possible het. So pos hets, or possible hets, can be bred to confirm whether or not they carry the gene. If you do a breeding with a possible het and they produce visual hypos, then you know that you have proved out your possible het. You have proved that it did carry through the gene, and it's no longer a 66% possible, it's a 100% het. So trans works the same as hypo for all these examples as well. You'll see no matter the pairing, it all functions the same way as the hypo gene did. The only way to get 100% hypo or 100% trans offspring is for both parents to be that trait. So that means when you breed a hypo to a hypo, 100% of the babies are hypo. If you breed trans to trans, 100% of the babies are trans. Now, what about Dunner? Dunner is a dominant gene. So if one parent is a Dunner, half of the babies will be Dunner. There is no such thing as het for Dunner, but sometimes the normal siblings can have slight pattern changes. It's just that they either are Dunner or aren't. So we can confirm this with our Punnett squares. We're going to input a Dunner at the top with a DN and a normal on the side with NN, and you can see that half the babies are Dunner. There isn't a super form of Dunner like with Leatherbacks and Silkies because the gene is dominant, not co-dominant. But the double D Dunners can, in theory, produce all Dunners when they breed with another animal. Now, here's where it gets complicated when we're looking at combinations, but realistically, if you understand what we just covered, then you'll have no problem with moving forward. If you don't understand it yet, go back, rewatch it, or watch someone else's video. Maybe I'm just bad at explaining. Now, the way that we do it is still going to be the same. We're still going to fill out the Punnett square by bringing the parent's genes down and across throughout the table. Now we just need to include more information. So we can start with a hypodunner. Hypodunner in this case is going to be represented by 2 H's, just the same as before, and 1 D. And then we're going to breed that to a normal, which is going to be 2 N's as before. We know we only need 1 D from the Dunner, and we can leave out the N that goes with the Dunner's D to make things a little bit less complicated. So we'll set it out as you can see and fill out all the squares as normal. Bring those letters down and across. All the babies are het hypo and half of them are going to be Dunner as well. And we'll leave that on the screen just a little bit longer so you can really see what has happened here and take in what's going on. So now we can do it with a trans leatherback to a het trans as well. Fill out those squares, and I'll leave this on the screen again so you can see what's going on with what we've produced. So 1/4 of the babies are going to be trans leatherback. That's that top left corner. We've got TTL trans leatherback. 1/4 of the babies are going to be trans. That's the right corner. That's double T, just trans, nothing else. 1/4 of the babies are going to be het trans leatherback. That's going to be the bottom left corner, T and L. So T N together is going to be het trans, and then the L for the leatherback. And then the last quarter is going to be het trans, just simple, T and N. As always, I reply to my comments, so if you do have any questions, feel free to leave them below, but now you have the basic understanding to do that with any possible combination. So if you do have any questions, again, feel free to comment them down below. Alternatively, I am one of the people that is on the Arachnids Unleashed Facebook page, which I'll link in the description. You can send us a message on there and I'll make sure I'm the one that responds to that message, not one of the other people that controls the page. I do also have Instagram. I'm just horrible at using it, but it's Aussie Unleashed if you want to send me a message on there if you don't have Facebook. But yeah, if you've been wondering what all the bumping and knocking and scratching is throughout this video, I have filmed this entirely in the reptile room. We've got some of our new additions behind us, which is a pair of 2 young angle-headed dragons in a totally bioactive tank. I so need to do a video on that, but everything has just been full on. Some of you know I've been recovering from a wrist injury. This video and some other videos have been in my drafts for ages, honestly. I just haven't been able to get around to posting stuff. My hand went a bit downhill and stuff like that, but this is real-time, real-life me, filming this now at the moment. I want to do snakes genes video. I'm also willing to do other genetics videos on request. I just mostly know about the beta dragons and like the carpet python. Words are hard. Beta dragons and carpet python morphs. But I can also cover like how gold chin works in blackheads and stuff like that. I think that's pretty much it. I've missed doing this, and you'll notice a lot of the recent videos have been more to do with the tarantulas and stuff. That's not always going to be the case. It's just what I've had content of to upload because we took over an entire other person's arachnid collection and there were mislabeled things. All the tanks needed to be redone. It's been an absolute nightmare. Thankfully, Dee has done most of it. I've filmed what I can, or Dee films while I do the things I can do with the restrictions of my hand. But yeah, I hope you guys enjoyed watching. I hope I helped explain it to at least somebody out there. But yeah, have a great night.